Okay, so today I want to do some general properties of equivariant cohomology. This morning I sent you chapter 2. Did you get it? If you didn't get it, you can just write me. Okay? Yeah. So we want to know what the homotopy quotient looks like. Okay? And there is one simple case. Okay? When we can actually see the homotopy quotient. Okay? That's when the group acts freely on the space. So if a topological group G acts freely on a topological space M, such that M projecting to the quotient is a principal G bundle. Then the homotopy quotient is weakly homotopy equivalent to the quotient M mod G. Okay? So what does it mean to act freely? To act freely means that the stabilizer of every point is the identity. Okay? And what does it mean to be weakly homotopy equivalent? Yeah. That there is a map which induces an isomorphism in all homotopy groups. Okay? So it's a little bit weaker than homotopy equivalent. But if these are CW complexes, then weakly homotopy equivalent is the same as homotopy equivalent. Okay? Okay, so so to prove this, I use Cartan's mixing diagram. So Cartan's mixing diagram is this one. You have EG cross N with the two projections, and then this maps to the homotopy quotient Mg. This maps to the usual quotient M mod G. Okay? So that's Cartan's mixing diagram. And our assumption is that this is a principal G bundle. So in a principal G bundle, G acts freely on the right on the space, okay? And so if this is a principal G bundle, what can you say about this map? This is a fiber bundle with fiber EG, okay? So Cartan's mixing diagram says that Mg mapping to M mod G is a fiber bundle with fiber EG. And if you have a fiber bundle, then you can look at the homotopy exact sequence of the fiber bundle by the homotopy exact sequence of the fiber bundle, you have pi k of EG mapping to pi k, pi k of the fiber mapping into pi k of mg into pi k of m over g into pi k minus 1 of EG. Okay? But EG is contractible, so this is 0 and this is 0. And this sequence is exact. Okay? So that means this is an isomorphism. Okay? If you have an exact sequence, with 0 here, that means this map is surjective. The 0 here means this map is injective, so it's an isomorphism. Okay? Okay. So so if you have a free action, then it's easy to see, well, then you have the weak homotopy type. So let's look at an example. So S1 acts on S1 by rotation. If you think of them as unit circles in the complex plane, then it's just multiplication. Okay? So by say lambda dot x is lambda x. Okay? So where lambda and x are both in S1, and that's the unit circle in the complex plane. So they're complex numbers, so we can multiply them. So S1 acts on S1. So is this a free action? Yeah, because lambda, okay, for each x in S1, lambda x equals x implies that lambda is equal to 1. So the action is free. Okay? And so what is the homotopy quotient? Well, now, this proposition says that it is weakly homotopy equivalent to the quotient S1 over S1, and that's a single point. Okay? So that says this has trivial homotopy groups for all k. Now, if you knew that this were a CW complex, then you would know that it has a homotopy type of a point. Okay? But, is this a CW complex? So, what is it exactly? What is S1, the homotopy quotient of S1? So we look at the definition okay? To get the homotopy quotient, you take, ES1, a contractible space on which S1 acts freely. You cross it with S1, and then you take the quotient by the diagonal action, okay? Now, what is ES1? It's, do you remember what ES1 is? It's S infinity, right? It's ES1 is S infinity. Okay. Okay. So, can you guess what this is?
S infinity.
Yeah, it's S infinity because you can map this to S infinity, right? Because an element here is an equivalence class of ES, okay? Where S is in the circle. And you can map this to, you want something that's well defined. Now this is also equal to EG G inverse S, right? All the equivalent points look like that. So what do you think this map should be? ES, yeah. You see, S1 acts on the right on S infinity. You can multiply them together, and this maps to the same point. So it's well defined, okay? And then, so there's this map, and then there is an inverse map. Okay, so an element of S infinity is E. Now, what should the inverse map be? E1. Okay. Okay. Then these two maps are well defined and they are inverse to each other. Okay. So, yeah. So S1, the homotopy quotient of S1 by S1 is S infinity. Okay. And yeah, it's contractible. It's a CW complex too. Yeah. Yeah. Okay. So, it's which has a homotopy type of a point. Yeah, the reason I do that is that now I would like to see what S2, what the quotient of S2 by S1 is, okay? The homotopy quotient of S2 by S1. So, let S1 act on S2 by rotation about the z-axis. So this is our usual example. We rotate about the z-axis. There are two fixed points, P and Q. And we know that the homotopy quotient is always a fiber bundle over BS1, right? From Cartan's mixing diagram. this is a principal bundle, so this is a fiber bundle with fiber M. Okay, so this is a fiber bundle with fiber S2. Okay. And yeah, so if you can picture it this way. Let's say, now, BS1, what's BS1? CP infinity. So BS1 is CP infinity. That's your base. And then you have a fiber bundle over it. So that means, you know, about each point you have a two sphere. That's not a very good picture because it's actually not a trivial fiber bundle, you know. So yeah, here's another way of picturing this homotopy quotient. Okay. So, another picture. Okay. Now, let's first look at the orbit space. I mean, this action is not free because it has these two fixed points, but it is free everywhere else. Okay? Now, what is the orbit space? The orbit space of the orbit space is S2 divided by S1. So, yeah. What's that orbit space? Yeah, it's the interval, right? Because the orbit of this point is itself, and the orbit of points here is the horizontal. Each horizontal circle is an orbit. So the orbit space is the closed interval. Mm-hmm. Now, if you take out these 2 points, then the action is free. Okay? So, the action of S1 on S1 minus PQ is free. And in fact, S1 minus the 2 points, S1 minus the 2 points, it's...
S2 minus...
Oh, sorry, S2. Yeah, right, S2. Thank you. Yeah, S2 minus the 2 points, it's a product bundle over the open interval, right? So it's equal to minus 1, 1 cross S1. Okay? So, yeah. And then, yeah. So now we can look at, the homotopy quotient. See, when you take the homotopy quotient, you're doing it fiber by fiber. You know, like every fiber is a S1 space. Okay? So let's see, S1 minus PQ. Now, when you take the homotopy quotient by S1, it's minus 1, 1 cross S1, and then take the homotopy quotient. And this is the same as minus 1, 1 cross. You can just do the you just this acts on this space by acting on each fiber. So it's this. Okay? And this is minus 1, 1 cross the homotopy quotient of S1 is S infinity, which is a contractible space. So this has the same homotopy type. It has the same homotopy type as a point, right? Because both of these are contractible. But I can just contract it along the fiber, and then it has, so I can picture it as having the same homotopy type as minus 1, 1, as the interval, okay? So when I take the homotopy quotient, I mean, this part here just gives me the interval. Okay? And then, you see, S2, it's a disjoint union of P with S2 minus PQ with Q. Each of these is an S1 space, okay? And when I take the homotopy quotient, so I take the homotopy quotient of P, I take the homotopy quotient of this, and then the homotopy quotient of Q. Okay? Okay, so what is the homotopy quotient of P? A single point. It's the classifying space, right? Because the homotopy quotient of P is ES1 cross P divided by S1, and that is isomorphic to just ES1 over S1. Okay? There's an obvious isomorphism, and that is BS1, and that's CP infinity. Okay? Yeah. So the picture of S2, S1, okay, is, well, so it has, it's the disjoint union of CP infinity with this, okay, which is minus 1, 1 cross S infinity, and with CP infinity, okay? And so this has the same homotopy type as you have CP infinity and then this is just an interval, the homotopy type of an interval, an open interval, okay? And then you have another CP infinity. Okay? Yeah. So this homotopy quotient, it has a homotopy type of a dumbbell. It looks like this. Okay? each fixed point gives you a CP infinity, and then the rest of the sphere gives you this line segment. Okay? And now this, this has the same homotopy type as, well, you can, move the two ends together. So, which has the same homotopy type as just a CP infinity and then another CP infinity. Okay? The wedge of two CP infinities. Now we can verify this by computing its cohomology. Okay? So you can compute the cohomology of either this or this. I think it's easier to compute the cohomology of this. Okay? So, so let's compute the cohomology. Okay, so okay, now the obvious way to compute the cohomology of this space is to do what? What technique do you use to compute the cohomology of this? It's got two parts. The Meyer-Vittora sequence, right? So you call this part the open set U, and this part the open set V. Okay. So by the Meyer-Vittora sequence, now this is the way I do the Meyer-Vittora sequence. I start with the manifold, not the manifold, the space. Okay, so this space, let's call it X. X. And then I restrict the forms on X to U, disjoint union V. And then I restrict them to the intersection and take the difference. Okay. So I have H. Let's do how about H4, H3. Okay. And then H2, H1, H0. Okay? And we just fill in what we know. Okay? What's H0 of X? Let's use integer coefficients. H0 of X is Z, because it's connected. Okay? And U and V are connected, so I get Z plus Z. The intersection is connected, so I get Z. And this, this is an exact sequence. So you're going to start with 0 here. Okay. Because this is surjective, so there's a 0 there. And then H1 of U, now U has a homotopy type of C infinity, and so what's H1 of U? 0, because we already know the cohomology CP infinity, it's Z in all even dimensions, right? So then it's H2 will be Z plus Z, H3 is 0, H4 is Z plus Z. Okay? And then the intersection is contractible. So it's going to be 0. Yeah. And, right, so then you have this, this 0 goes to, so here it has to be 0. Yeah, so these two columns have to be the same, right? This has to be Z plus Z. 0, Z plus Z. Okay? Yeah, so now we have the cohomology. So the cohomology of X is Z in dimension 0, 0 in odd dimensions, and then Z plus Z for K even and greater than or equal to 2. Okay? And you see that this agrees with what we calculated before. So last time, we showed that the cohomology of the homotopy quotient of S2 by S1 is the polynomial ring ZU plus Y times the polynomial ring ZU, where U, the degree of U and the degree of Y are both 2. So you see, these two results agree, right? In dimension 0, you have only Z, but in dimension 2, you have U and Y, and then beyond that, you have U square, YU, U cube, YU square, and so on. Okay? Yeah. So these two results agree. Yeah. Okay.
Slightly how S infinity is moved into the CP infinity does not really matter, or does it? Because that is just disjoint union and the calculations. Use, the middle one is an interval, but at the endpoint there should be still S infinity on the endpoint, and that S infinity should be glued onto CP infinity, I suppose. But that how it moves together does not really matter.
S in. I don't lose S infinity. I just take the because this is the same homotopy type as an interval. So I'm just looking at an, let me see. So yeah, I'm just saying this has the homotopy type of, so I have contracted this to just an interval, and then there's just one endpoint, so there's really no question how you glue them together, right? Yeah. So I don't try to glue CP S infinity to CP infinity. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Although
take them apart and then deform it, and then
yeah.
since there's
Yeah.
only one choice of
right.
bringing them back together.
Yeah, yeah, yeah. Mm-hmm. Mm-hmm. Yeah. Well, I guess there must be some way of gluing S infinity to CP infinity. Yeah.
Portion map.
Yeah, because you have this map, you have S2, S1 mapping to the quotient, right? To S2 by S1. So we always have this map in the Cartan diagram. Now, it's not a fiber bundle. It's not locally trivial because there are two fixed points. But yeah, so the fiber, okay, so there is the map. There's always this map from Cartan's mixing diagram. And so whose fiber above one, because this is minus 1, 1, whose fiber above 1 is S infinity, and whose fiber above minus 1 is S infinity, and then over the open interval, no, sorry, the fiber above 1 and minus 1 is CP infinity, right? It's, because you have a fixed point. So, yeah, that's the fiber above P and Q, above 1 and minus 1. And over minus 1, 1, so it is minus 1, 1 plus S infinity. Yeah, so it's already glued together in some way, you know. Yeah, but this part is it has a homotopy type of an interval. Yeah.
So somehow you have a homotopy which fixes the both ends CP infinity and contracts the middle interval, the interval cross C infinity.
Right.
To
Yeah.
the linear interval.
Mm-hmm. Yeah. Mm-hmm. Or you could just contract this whole thing to a single point like this. Right.
Means there's a homotopy which fixes the antipodal CP infinity. Do I have to do I need to fix it? Yes, from this I cannot see whether the homotopy is continuous or not.
Yeah, okay, that's a good question. So I guess, yeah, so somehow, yeah, S infinity is glued into CP infinity. And then you just, so here's CP infinity. And then you have some S infinity glued there. And so you just contract this part, right, to a single point. Yeah, and it's contractible, right? So it doesn't really affect the homotopy type of the N. Okay? Yeah. Okay. So next I want to just prove some very general properties of equivariant cohomology. So, on polarity. Okay? Okay, so a G equivariant map is sometimes just called a G map for short. Okay? And a G map F of G spaces induces a map of homotopy quotients in the obvious way, right? Because this is EG cross N and then divided by G. This is EG cross N divided by G. So you just take En to EF of N. Okay, and you have to show that it's well defined. Now this is the same as EG G inverse N, and that goes to EG F G inverse N. But because F is a G map, this is EG G inverse F of N. Okay. So that's equal to this. And so that proves that it's well defined. And so then FG induces a ring homomorphism in cohomology. FG star. Okay, it goes from the cohomology of MG to the cohomology of NG. And now we have this diagram. So N to M, both of them map to a single point, which you can consider as a G space, right? G acts on a point trivially. So this will induce maps in homotopy quotients. And then this will induce a commutative diagram of ring homomorphisms. the cohomology of the homotopy quotient, that's the cohomology of a point, it's the cohomology of BG. Okay? So this is, if this is F, this is FG, this is FG in star, and let's call these two maps alpha and beta. So alpha and beta give you the algebra structure, right? Where H star BG serve as scalars. Okay? And so what does this say about FG star? FG star, if you take an element U here and an element X here, then you can look at FG star of alpha U X. Okay. And because FG star is a ring homomorphism, this is FG star of alpha U, FG star of X, and then FG star alpha is beta, so this is beta U FG star of X, okay? But alpha and beta are the maps that give you the algebra structure. So this is FG star of what we call U dot U times X. And this is U times FG star of X. Okay? So what this says is that when you multiply by U and you take FG star, that U just comes out. And therefore, this FG star is a H star BG algebra homomorphism. Okay? The scalar just comes out. So FG star from the cohomology, equivariant cohomology of N to the equivariant cohomology of N is an H star of BG algebra homomorphism. Okay. Okay. And so what you get is a functor. You have so equivariant cohomology is a contravariant functor from G spaces and G maps to H star of BG algebras and H star of BG algebra homomorphisms. Okay? It's really the composition of two functors, right? You first take the homotopy quotient, then you take the cohomology. So you end up with this functor. Okay? Okay, let's take a break for 10 minutes. And then we'll start again.
want to ask about
Yeah.